Welcome. So we have a compressor and it's providing flow into a 10 cubic meter tank. The mass flow rate here is given by this equation, and so the density in the tank starts out with a value of rho 0, and that value is 2 kilograms per cubic meter, and at the end of the problem the density is increased to twice that initial density, so we're going to go from rho 0 to 2 rho 0. The problem statement tells us to assume the density is uniform throughout the tank. So I'd visualize the tank as some kind of volume region. I just picked a cube, and this would be about 2 meters on a side because 2 cubed is 8 cubic meters and the actual volume is 10. And the mass flow rate initially is 0.5 kilograms per second, and I got this by putting numbers into the formula. And when the density is doubled, this goes down to 0.25 kilograms per second. And this makes sense. When the density in the tank is larger, the compressor's less able to pump air into it. Initially, the density of the gas in the tank is 2 kilograms per cubic meter, and then at the final state it goes to 4 kilograms per cubic meter. And so very important, I see a well-defined state 1 and I see a well-defined state 2. How am I going to solve this problem? Well, I see an inflow and I see mass increasing inside the tank, and so that clues me in that I should try the continuity equation. And so here's the general form of the continuity equation. There's no outflows. There's one inflow. Oh, there's inflow into tank, and the mass will increase. And so it appears that I can apply the continuity equation to solve this problem. And there's a big hint here, and that is the gas goes from state 1 to state 2. And anytime I see a problem where there's a state 1 and state 2 like this, I know I'm going to need to integrate the continuity equation. Let's go ahead and get started with the problem solution. Here's my documentation. Notice here how I clearly defined the change in state. And notice here and here, I introduce variables instead of numbers. The reason is that I've learned that this makes my algebra a lot easier as I go through a problem like this. Here's my goal. To reach my goal, I'm going to apply the continuity equation. So I sketch my control volume, and I use symbols to indicate the inlet mass flow, and right here I'm showing the accumulation of mass inside the control volume as the compressor pumps gas in. I write the general form of the continuity equation. There's no mass flow rates out, and there's only one mass flow rate in, so that goes to m dot. And then the mass inside the control volume is the density of the gas times the volume of the tank. And I should also include the mass of the tank itself, but when I take the time derivative, this term will go to 0, so I usually do not write it down. So the reduced form of the continuity equation is right here. The time rate of change of the mass in the control volume is equal to the rate of mass flow in. Now the volume of the tank is constant with time, so it can come out of the derivative. The density inside the tank varies with time, so I have to leave it in. So I pull the volume out, and that gives me this equation. Then I do term by term analysis, and this shows that I have one equation and one unknown. Let's go through this real quick. The volume of the tank right here is known. And when I have a derivative, like this term right here, I treat the dependent variable, which is density in this case, as a known variable, and the independent variable, which is time, as an unknown. So time is my unknown, and then the m dot naught is known from the formula, and rho naught is a given parameter, and then rho here is my dependent variable in my derivative back on this term, so that's a known variable. So that's a little bit complicated, but the key idea, I can count variables, and there's one equation and one unknown. I'm ready to solve this problem. So my plan is to separate variables And this is the name of the technique as it's taught in a differential equations course. And it's a real simple idea. If you haven't seen that, I'll show you how to do it. So after I've separated variables, I'm going to integrate both sides of the equation from state 1 to state 2. Let me show you how that looks. So here's the original equation, and the key idea, here's my dependent variable, d rho. I take all things that involve rho and put them on this left-hand side. So rho itself comes over here, and then I take dt and move it to this side of the equation. So after I've separated variables, here's my result. And what you want to notice, this whole group of parameters in this bracket is a constant, and everything to do with time is on this side of the equation, everything to do with density is on this side of the equation. This is the key idea for separation of variables. Now, you can't always separate variables and solve a differential equation, but often in engineering you can solve a differential equation by this technique. My next step is to integrate this side of the equation and integrate this side of the equation. And at state 1, the density of the tank is rho 0. At state 2, the density is 2 rho 0. And at state 1, the time is 0. And at state 2, the time is t final. And so if I clean this up, here's the resulting equation. And now I have an equation like x dx, but it's rho d rho. That's easy to integrate. And I have a constant here which can come out of the integral, and then the integral of dt, which is very easy to integrate. So after I do the integration, I get this equation, and my next step is I'm going to evaluate the limits of the integration there and there, there and there. So after I've evaluated the limits of integration, here's my results. And there's a lot of kind of algebra there, but you can pause the video and have a look at this. I believe that's correct. So lastly, I take that long equation we just looked at and do algebra on it to solve for t final, and I get this equation here. Then I substitute in numbers, carry and cancel units as always, and the calculation shows that to go from state 1 to state 2 will take 60 seconds. This concludes the example. I hope you found this useful. We'll see you next time.